Hello again, welcome back to the mini course. We're going to spend a lot of time in this mini course thinking about surfaces inside of four manifolds. So let me kick off lecture 2 by discussing a concrete way to think about these intersections. So we saw by transversality up to isotopy, we can assume that surfaces in a four manifold intersect in isolated double points. So I want to talk about how to picture them. So as a model intersection of surfaces in a four manifold, let's consider the model four manifold, namely R4. I want to think about R4 as the product of R3 with a time coordinate. And I'm going to picture for you the intersection between the XY and the ZT planes at the origin in R4. So because of this decomposition, I can think of R4 as a sequence of R3 slices, one per time coordinate. Here's a few of them drawn out for you. So each of those panels is a copy of R3. And let's see how these planes show up in this decomposition. So the XY plane, that's going to show up just in this middle time slice. It's showing up as a nice flat plane there. The ZT plane is going to show up in a slightly weirder way. In this middle time slice, it shows up as that line at that line segment. It's the Z axis in this picture. But then as T changes, I'm going to see other vertical line segments, vertical axes, as I move backwards and forwards in time. So if I take all of these vertical lines together, they're going to trace out for me the ZT plane. And then I see that the intersection point between the red plane and the blue plane is precisely that point at the origin, as I expected. So now in this model, we can describe things very concretely, but it turns out, well, part of my definition of transversality is that each point of intersection has a nice R4 neighborhood where I basically see this local picture. So that means I can imagine that that is a point of intersection between two transversely intersecting surfaces, maybe a self-intersection, and there will be a little local neighborhood where the picture looks just like this thing that you're seeing in the screen. Okay, so I want to, since we have this method of thinking about four manifolds as sliced up in a movie of three-dimensional slices, let's quickly make sure we're on the same page about how to picture familiar shapes and spaces when they're sliced up like this. So this might be slightly elementary, but it will get us all set up to do some more complicated things. So first of all, if I look at the disk D2, I see that it's made up of these line segments. There's this equatorial line segment in the middle that's a diameter. And then as I move upwards and downwards, I see these littler line segments. So the radius shrinks and shrinks until I get these degenerate things in the top and the bottom, the north and the south. Similarly, I could think about D3. And D3 is made out of slices that look like D2. Here's that equatorial D2 slice. So this thing is filled in, by the way. This equatorial D2 slice takes up the entire diameter. But then as I move upwards and downwards, I see these radius shrink until at the top and the bottom poles, I see these degenerate disks, namely just points. Okay, so those are disks, but I could also think about spheres like this. So the same picture now just the boundary tells me that S2 is made up of a sequence of S1s. Here's the equatorial S1, then it shrinks in radius as we go upwards and downwards until we get the degenerate things at the north and south poles. And then similarly, we can think about S3 like this. Well, S3 is the one-point compactification of R3, so I'm going to draw a picture of R3 basically. So in this case, I should see a sequence of S2s. Here is, for example, the unit sphere S2 centered at the origin of R3. And then as I move outwards, these spheres increase in radius. As I move inwards, these spheres decrease in radius until I see these degenerate points. One of them is at the origin. That's the sphere of zero radius at the origin. And then there's going to be another one at the infinity point. And so this is a way of thinking about these familiar spaces sliced up into pieces, which will come in handy in the next slide. Speaking of which, let's continue visualizing surfaces in four manifolds. So I want to think a little bit more about that model point of intersection between surfaces, namely this origin point in this picture. So I want to think about a little B4 neighborhood around that point. So just like we saw on the previous slide, B4 can be sliced up into little pieces. It's going to have this equatorial B3, and then littler B3s going off to either side until they shrink down to points at either end. So what I have highlighted here for you is a B4 neighborhood of that central intersection point. Okay. So the boundary of this B4 is, of course, an S3. And you can see that S3 has this nice decomposition as these spheres that I have drawn here. There's the middle one that has the biggest radius, and then it's shrinking off to points on the two sides. So I want to think about how that S3 intersects my surfaces, given here in blue and red. I'm calling them P and Q. By transversality dimension reasons, I know they're going to be one-dimensional manifolds, but let's see precisely what they are. So the intersection of this S3 that's still highlighted here with P, that's going to be this blue circle. It's the one that looks like that. That's happening all in that central time slice. The intersection with the red surface is a bit weirder. It's given by this circle that is traced out by these 2 points. And that should have been obvious from the picture of S3 that I had drawn over there earlier. And so this looks a bit weird, but this is in fact a picture of S1, where I've sliced S1 into a sequence of S0s until it shrinks down to these degenerate points at the north and the south. Okay, and then an exercise for you is to see that this one manifold that I've described in S3, this is actually the Hopf link, the link that's pictured over here on the top right. To do this, you should think about here I had an unusual picture of S3. You should think about the correspondence of that picture with the usual picture of S3, maybe as the one-point compactification of R3. But what I do want to talk about in the lecture itself is what are the components of this. So we saw what the components are. I'm going to say that, in fact, this blue circle that I have here, that is something I'll call the meridian of the red surface Q. So what does meridian mean? Meridian means that this circle is the boundary of a disk that intersects Q at a single point. In this case, that's very easy to see. Here's the disk. The point of intersection is precisely at the center. So that is the definition of meridian for a surface in a four manifold. You may be more used to thinking of meridians of knots and links in S3. It's the same definition, just one dimension up. So this blue circle that I have, the blue component of the Hopf link, that's a meridian of the surface Q. It turns out that the other circle, the one that I have in red here, is also a meridian, but this time of P. One way to think about this is that the situation is entirely symmetric. It's just that I've drawn it in a slightly asymmetric way, so you could just flip perspective, and then the red circle would show up super nicely. But instead, I kind of want to show you what the meridional disk looks like in this version. So remember, these red circles are showing me these red dots show me the red circle. And the meridional disk is precisely the union of these line segments that I'm highlighting right now. These don't look like a disk perhaps, but it's precisely a disk based on what we saw in the previous slide. And even now I see that this disk, which is split up into line segments, I want to say that it intersects the blue surface P at exactly one point. And of course it does. It's that point of intersection at precisely the origin. Okay. And so the moral of this slide is that if I take two surfaces that are intersecting at a single point, the meridians of those surfaces, they form a Hopf link inside of that S3 boundary of a little B4 neighborhood. Okay. So now I want to continue on with this a little bit further. So I have these meridians of P and Q. These are S1s, and I want to take the product of them. It's a product of S1s. It's going to be a torus, and it's going to be, this one's an important one, so it gets a name. It's called the Clifford torus. So what's a picture of this? So here I have the red and the blue circles from the previous slide. When I want to take the product, that means I should take this blue circle and I should see a copy of that at each point of the red circle. So I've drawn that here in purple. So you see that these purple circles, they travel all the way around in this neighborhood. But I have one copy of it per red dot. So in particular, I have an S1's worth of S1's, so it's a torus. So that here is a surface called the Clifford torus. This will be important coming up in a moment, even in a future part. So there it is. Okay. So continuing on with our discussion, we now know something about how to represent surfaces in a very concrete way within four manifolds. So I want to go and talk about how to think about the Whitney trick for surfaces in four manifolds. So in Smale's proof of the H-Cube-Ordison theorem, we saw that this was a key step that kind of did most of the proof for us. And so we want to mimic that proof. So we want to see to what extent does that hold in dimension 4. So in Smale's proof, when I described the Whitney trick, I drew a picture like this for you, and it was a bit schematic. But now a picture like this is totally concrete. So there's this middle slice, which is telling you that the red and the blue surfaces intersect and isolate at double points. Then these red lines that are going backwards and forwards in time, these trace out for you a surface that's a red surface. It's just that in the middle time slice, I only see the red surface as a line. And I have these points of intersection, P and Q. And quick reminder of the Whitney trick. The Whitney trick said that I should find for myself a circle, which goes from this little p to little q along blue, and then back along red. So that is a circle in my manifold. In this case, it happens to bound a disk, a nice embedded disk, which I can see that I've highlighted. And the Whitney trick says that I should take 2 copies of this disk and use it to guide an isotopy of the blue surface so that these intersection points get canceled. The end result of the isotopy looks something like this. I should take 2 copies of the Whitney disk, and I should use it to form this bubble that sits on top of the blue surface. This is what I called the T-cozy last time. And you can see that if you do this, if this is the result of the isotopy of the Whitney trick, the Whitney move along that disk, then those 2 intersection points, little p and little q, get canceled and are no longer a part of the picture. So this was a way of removing those extraneous algebraic intersection points that we don't like. So, okay, so our question is, to what extent can we do the Whitney trick in dimension 4? So if my ambient space is simply connected, then I can find for myself a map of a disk bounded by the Whitney circle. So I still have a Whitney circle that looks like this. But I'm assuming I'm in a more general situation, so I don't necessarily have that obvious disk that's staring us in the face in this nice case. If my ambient space is smooth, then I can also assume that this disk is immersed, so it has isolated double points. But I still have some questions that I need to answer. In particular, I need to know that my disk is embedded. I need to know that the interior of the disk lies in the complement of P and Q, so that when I do my isotopy, I actually remove the 2 points of intersection and I don't get any new ones. And then lastly, there's a question here about framing, because remember, I took the Whitney disk and I pushed it off of itself to get 2 copies. So whenever I do something like that, framing becomes a question you have to think about. I'm going to try to avoid thinking about it as much as possible, especially for the lectures. I'll try to write something about it in the typed lecture notes. But it is an important point, but it's difficult to talk about everything in an hour. All right. So I want to address all of these questions in turn and see if we can answer them. So just to get it out of the way, how about framing? It turns out there's this process called boundary twisting, which says that we can perform this. If you give me a disk delta, and I can twist it in some way to ensure that the framing is okay, whatever the framing is, but I have to pay a price, and the price is that I'll get more intersections of delta with P and with Q. But that's the purview of the second question, which I already have to answer anyway. So that's not that big a price to pay, because we have to answer that problem at some point. So up to boundary twisting, let's say that the framing is fine. Let's continue to ignore this as much as possible. What about this interior intersecting P and Q? Well, what we did in the proof of Smill's theorem is we said, well, let's assume that the fundamental group of the complement is trivial. And so when you have this disk just came out of a simple connectivity assumption anyway. Now you can just apply this simple connectivity assumption. So these two things essentially tell you that the answers to these last two questions, we can sort of get those. That's not too bad. One question you might have is, how should we order these two things? This is something that is worth thinking about. I'm going to avoid it. But in the cases that we are interested in, we can essentially make it so that these two are not questions we have to worry about. This top question, though, that's an important question. This is a question that's going to be a big one. And so that brings us to our refined question of, suppose I have an immersed disk, can I improve it in some way to an embedded disk? And now if you know something about three-manifold topology, this should remind you of something like a Dean's lemma. Like, if I have an immersed disk, do I know that there's some embedded disk as well? And of course, all of this stuff should be asked relative to the boundary. Specifically, I have some Whitney circle in my mind and I don't want to mess with that. So whatever I'm doing, I should be fixing the boundary, and then everything else is in play, but the boundary doesn't get to change. Okay, so here's our question, like, when can we replace an immersed disk by an embedded disk? First, some sadness, we can't always do this. So you can't, there's no analog of Dean's lemma in total generality in dimension 4. There's a nice example that shows this. So if you think of a knot, any knot inside of S3, it's the boundary of an immersed disk in B4. That just comes from the fact that B4 doesn't have any homotopy in there. It's very simple space. On the other hand, if I have a knot in S3, which is the boundary of a smoothly embedded disk in B4, we call that knot smoothly sliced. So the picture of that is in this bottom left. I have my knot K inside of the boundary of B4, which is an S3. And if there's some smooth disk somewhere with boundary K in B4, we call my knot smoothly sliced. It turns out that not all knots are smoothly sliced. So for example, here's the trefoil knot. That guy is not sliced, but it is the boundary of an immersed disk. So in particular, that is an immersed disk that cannot be replaced by an embedded disk, at least not a smooth one. Okay, so that's a little bit discouraging, but it turns out we can do something. And what is the thing that we can do? The thing that we can do is the disk embedding theorem. Now this is the key insight, the key result of Friedman. It's not a stretch to say that this is the theorem that's behind every example of exoticity for manifolds that we are aware of. So this is a pretty big deal. So what is it? Let's sort of work up to the statement of this theorem. Part of it is this thing that we already have. I have an immersed disk inside of a four manifold. I'm assuming that it's smooth and simply connected for now. I'm going to give a preliminary version of this theorem for now, and later we'll see a more general version. I'm also assuming that the map F is already quite nice on the boundary. So I have an embedding restricted to the boundary, but an immersion. So there are potential double points everywhere else. So this is not enough. I need some extra information. And what will that look like? Turns out the extra information is in the form of a partner for F. This is something that's usually called an algebraically dual sphere for F. I've drawn it here in purple, so let's see what I require of it. So first, I want to make sure that the intersections between F and G, algebraically, there's just one of them. So that means perhaps there's more, perhaps there's three, like in this picture, but these extra ones come in pairs, plus or minus, so they algebraically cancel. I also want that the algebraic self-intersection number of G is trivial. And what that means is maybe G has these self-intersections, namely in this picture, these two, but these also should have canceling signs, plus and minus. And then lastly, I'm not going to spend much time talking about this. I want this G of S2 to have a trivial normal boundary. Basically, I'm going to take lots of push-offs of this guy, and I want to do that in some controlled manner. Okay, so those are the hypotheses of the disk embedding theorem. This is this extra bit of information that I have in my input. And the output of the disk embedding theorem in this very simple version of it is an embedding. So the theorem says that I can find for myself an embedding F bar, which matches up with F on the boundary. So nothing happened here. These portions remained the same, even including some framing information, which I have not written down. But there is a price that we have to pay, and the price is encoded in this word flat. So flat here means that the disk comes with a neighborhood. It has a neighborhood which is homeomorphic to D2 cross D2. However, there is no version of this theorem which has the word smooth that I can write down over here. And so this is where we lose category, by the way. So this disk that I find, this is not a smooth embedding. This is just going to be a flat embedding. And that's the reason why we have so much exotic phenomena in dimension 4 that we can see using this theorem. Okay. All right, so in a later part, I'll give an outline of a proof of this theorem. And in another part, we'll see how to apply this theorem to prove Friedman's H-cobordism theorem. In the rest of this video, I want to talk about this hypothesis. So to make the disk embedding theorem run, to make it fire, I need to produce for you some algebraically dual spheres somehow. And then the question is, where are those going to come from? Turns out they're going to come from Clifford tori somehow. I'm going to tell you how. That's the plan. So here I have a picture of a surface, a torus for now, which is capped, meaning that I have a curve on the torus, which is the boundary of a disk. I've shown you the embedded picture here. All of this will work with caps that intersect themselves, each other, but easiest to think about it with embedded caps. So that disk is called a cap for the surface. This thing is called a capped surface. So what I'm going to do with this guy is I'm going to cut the surface along this curve to which the cap is attached. It's going to split open. And then I'm going to cap off those two new boundary components with 2 copies of that disk of the cap. So this is what I'm calling asymmetric contraction. Sometimes this is also called surgery. It's a word that's used too often, so I'll stick to contraction. So I hope it's clear from this picture that the result of this operation, this is an S2. So I started with a T2 and I produced an S2 after asymmetric contraction along this cap. Okay. And now I can do this in a slightly different way. This is a bit harder to picture. Last time I had a cap along the meridian, but now I want a cap along the longitude. And so there's a disk bounded by that longitude. And just like last time, I'm going to cut the surface along the longitude. It's going to leave behind an annulus. And the 2 boundary components I'm going to cap off with disks. Now here, the 2 copies of disks are lying on top of each other, so it's not as clear to see, but this is once again a picture of an S2 that I produced from a T2. All right, so these are 2 different asymmetric contractions of the same surface. The contraction that I actually want to do, though, is something that's more symmetric. So I'm going to now have caps for a symplectic basis of curves for the homology of the surface. So in this case, a meridian and a longitude. And I'm going to do this contraction process using both of those curves. So first, I'm going to cut the surface along both of these circles. All right. And then I'm going to get a new boundary component. In this case, it turns out that the boundary component is connected. So it's a single S1. And you can kind of see that boundary component in this picture on the left. It looks like this. It's a bit hard to see, but it's a single copy of S1. And now I'm going to cap off that new boundary component with a thing. Last time I used copies of the caps. I'm going to use them again, but now in a slightly more interesting way. It's the caps. I'm capping off using this business over here. And so the piece that I'm using looks like this flower on this right-hand side. So let's explain how that fits together. There's this central rectangle that's showing up over here. That's right there. There are these 2 red flaps. These flaps get like folded upwards. So they make these bunny ears that are like up, pointing up. So that's capping off this portion of the boundary. And then there are these blue flaps. These guys are going to get folded over. So they're going to be lying on top of each other. Like there's one flap and then there's the other flap that's behind it. Okay. And so at the end of this process, I have something that is a bit more unusual to draw, but I hope that it's clear that that is another picture of an S2, just a weirder one. Okay. So here is a way that you can get from a capped surface, capped meaning both meridian and longitude have these caps associated with them, and then they get this S2 at the end. And then once again, I've drawn the picture just with embedded caps, but you can do this with caps that have intersections. It's just much more annoying to draw. And now you may be wondering, why on earth are we doing this super complicated contraction when we have the very nice contractions that we already did that were so much easier to work with? It turns out that the symmetric contraction has a very nice property. And I'm going to show you how that works with an example. The idea is that I want to work with, so I'm going to symmetrically contract a surface, a capped surface that's showing up here in this middle time slice. But I want to think about how this contracted object interacts with other surfaces in my four manifold. That's the key thing that's why we like the symmetric contraction. So here I have a picture for you of an orange surface. It's drawn backwards and forwards in time by these orange line segments, and that orange guy intersects the red cap in a single point. And similarly, I have this green surface given by these lines that intersects the blue surface in a single point. So I want to think about how those intersections develop as I do this contraction process. That's the thing I want to do. So the capped surface is entirely in this middle time slice, so I can do my contraction. Here's what that looks like. And that single orange point of intersection has doubled. It has become 2 points of intersection, one with each copy of the cap that I've used. And similarly, the green intersection has become 2 green points of intersection, one with each copy of the blue disc that I've used. So far, not very good because I've just doubled my problem. Now I have these extra intersection points, but that's where this pushing off operation comes in. So what I have is that this orange guy intersects the red caps, like the copies of the caps twice, but I can take that little segment and I can push it down. And when I push it down, I just avoid the caps altogether and I sneak in between the 2 copies of the blue caps. And so I've totally avoided anything to do with this contracted surface. And then similarly, I can take that little segment of green and I can push that upwards so that I just avoid these 2 copies of blue and I sneak in between the 2 copies of red and go on my way. Okay, so here's what that will look like. So in this middle thing, we see here's that green has moved upwards and then the orange has moved down. And so in this middle dimensional time slice, I no longer have any points of intersection between the contracted surface and orange and green. So that's super. And you should convince yourself that if we had done the asymmetric contraction, this would not have worked out very nicely. There is something else that we do have to worry about though. When I'm doing this geometric move on these orange and green surfaces, in this sort of sliced time perspective, I can't just do it on a single time slice. I have to do it in a neighborhood because otherwise I'm just breaking apart my surface. I have to do something in this nice, continuous, smooth, and ideally local way. And so because I've moved my green thing in the middle to look like this, I also have to move it similarly in an adjacent time slice and also in either direction. And then similarly for orange, because I've moved it downwards like this, I also have to move it downwards like this over here in the adjacent time slices. But I want to do a local move, so at the ends, I still have my previous picture that looked like this. And so this is something that we need to be really careful about. This is why it comes with a super large exclamation point. I need to do an isotopy. I need to push back orange and green so that they match up with the previous picture. And so as I'm pushing orange back up to where it started and green back down to where I started, there'll be a frame somewhere over here where green and orange will intersect. And then similarly, there'll be a frame somewhere over here, maybe at 3 epsilon over 2, where green and orange will intersect. And so what this contraction and push-off operation does for us is that it does make green and orange disjoint from the contracted surface, even though they intersected with the caps. But as a price, the green and orange surfaces now intersect each other. Good news is that these intersections are algebraically canceling, so they're going to come in plus and minus pairs, but they're still there. So there is still geometrically some new intersections that we have to deal with. But anyway, so this process tells us if you have a capped surface somewhere, you can do this contraction process, symmetric contraction always, to get for yourself a sphere, maybe an immersed sphere, depending on what your caps were like. And then because you've done symmetric contraction, you get some nice disjointness properties at the end as well. All right, so that is the end of our discussion of surfaces in this concrete way. Next video, we'll return to the proof of the H-cubism theorem. See you there.